Test. All right. What's up, Thickless, Imposter Sus? What's going on? All right. Let's do it again. Let's jump right into it. We got loops and conditionals. We got I say catch up, but loops and conditionals really should just be in lecture 2. I would never get to this in the first lecture. And then data structures is what we want to cover today. And if there is any time, we'll cover some additional examples. This is open-ended. This is just whatever examples I want to show. So let's do exactly that. And since it's the 11 a.m. lecture, I'm going to lecture in a live coding style. And, oh shit, I wanted to figure out how to do this. Pin, doc, float, no. I'm right. There we go. Clear. Clear. Face. That's where my face goes. Anyway, I don't have to worry about covering anything up. Okay. We can close this one. Collapse this. And get to it. Alright, so we want to do conditionals and loops. And I'm going to do this in... What's the best way I want to do this? I gotta figure out how to do this for every lecture. I think I'll go into a new package. I won't push any of the live code. I'm just, for the most part, duplicating the examples that are already in the repo. So I'm not going to push the live code, but I will create it in a separate package so I can use the same class names as the ones that are in the repo and in the slides. So plus minus is the one that we want to add. Don't ask again. Cancel. And let's do conditionals. So I want to create a new, and we're going to dive right into it. There's no time to have a slow, easy introduction. I already wasted 2 minutes. Let's do this. So public static, because every method is going to be public and static at this point in the semester. And this method is going to return a string. And what we want to do is return a letter grade based on a numeric score. So let's call this letter. And I have some integer score value, and we want to return the letter grade. Let's just put it in a comment here. We'll do a java.comment. So returns, I won't do full java.doc style, but returns the letter grade for the input score. 90 to 100. Is an A. 80 to 89 is a B. 70 to 79 is a C. 60 to 69 is a D. Less than, well, let me stay consistent. 0 to 59 is an unfortunate F. Okay, so that's what we want to build with this method. And we're going to do that by getting the tens digit of the score. So I'm going to create an int tens. And I want to get just the tens digit of the score. And to do that, I'm going to use our good old friend integer division. If I divide the score by 10, since score is an int and 10, I didn't put 0.0 here. That would actually give me an error. I just put 10. That's going to be treated as an int. So this will be integer division, and I'll get just the tens digit of the score. That's what I want to do here. That's because we have an int divided by an int. If I do 0.0 here, I have an int divided by a double. I do not get integer division. And the result of this division will actually be a double with the floating point, the decimal portion of the number, and I can't store that in a variable of type int. So I can't do that, things we talked about last time, but just reiterating that. And, oh, yeah, I keep thinking there's something I'm forgetting to say. I've been messing with the audio. The audio just sounds, when I play back the streams from Tuesday, the audio just sounds kind of crappy. I changed some settings, so if it got worse, definitely let me know. If you're giving me feedback, I can try to play with some settings during the lecture, but I just think the audio sounds like crap. I'm so mad about that. I have a Blue Yeti that I'm talking into. This is my second Blue Yeti that I've had, and I'm just starting to think that these are garbage mics, because I always have so much trouble just getting good audio with them. I have better audio on my laptop, just the built-in laptop microphone, than I do with this thing sometimes. I mean, I know they're an intro mic, but they should be better than my laptop microphone, I thought. But anyway, if I'll work on that throughout the semester. Hopefully we'll have good audio by the last lecture. But it's usable, it's functional at least. It's just not the quality it should be for this mic. And we want to return the score or the letter grade. Right now I'm going to return an empty string just because before we get too far into the method, I want to set up our calls for the method. So I'm going to set up my main method, and I'm going to have my, I'm going to call my method letter of, I'll try to remember the exact inputs that we have in the slides. Letter, and this will be a string that's going to be the grade, which I think we call result in the slides, but I'll call it grade here. It makes more sense. And then print out grade to the screen. So if the score is 98, we would expect that to be an A. And then I'm going to reassign grade to the result of letter of, so I forget what the exact number is, but it's in the 70s, so it's a C. And then S out grade. And then let's call it a third time, grade equals letter of 3. That's not the example I use in the slides, but we can deviate. Grade, as long as the key points are the same. Okay, so we have 3 calls to the method. We expect A, C, F being printed to the screen, and we can run this code just to get my formatting down here set up. It doesn't print anything. Actually, it does print something to the screen 3 times. It's printing the empty string with a new line character. So there's actually something going on there, but nothing interesting because we're just returning the empty string. This we'll talk about on Tuesday a bit more. We're not going to test using main methods like this. On Tuesday, we're going to start testing using unit tests. And this is something that I'll recommend is writing your tests first and then writing your code using the tests. So I have my test cases here just in a main method for now. And when you do that, you do have to write the method. Like the method has to exist, but it doesn't really have to do anything yet. So when you do that, you can what we call stub out the method. You don't even need this line here. Just stub out the method. Just return anything to satisfy the return contract, but it doesn't have to be anything meaningful. Just have something so these calls, your testing calls, will compile and run even if they don't return anything meaningful. But we're here to write this actual method. And we're here to talk about conditionals in Java. And I don't have a whole lot to talk about conditionals. It's a topic that you have to know coming into 116. There's no way you would pass your previous semester of computer science without knowing conditionals. So I'm just going to highlight these syntax differences for Java. And for that, there's really not much, but we will talk about them. So if, the way I want to do this is if tens is greater than or equal to 9, I know this student's getting an A, and I'm going to return A. And then our first difference, if you're coming from Python, is else if. This is going to be my else if statement. 10's greater than equal to 8. So if you're in the 80s, I know that's going to be a B. So the difference here is that it's else if. In Python, Python randomly deletes these 3 characters for some reason and just does elif, which is short for else if. It's still the same thing, but Python, for some reason, Python's very, Python almost reads like English sentences most of the time, but for some reason, when it comes to else if, they make that one more confusing than it should be. So that one's, just kind of strange to me, but it's one thing Python does different. And the other difference is braces. We're defining our code blocks using braces like this. Let me just run my formatter. Using braces like this instead of indentation. If this is, can I even do it like that? Like this. If this isn't indented, this code still is identical to what it is with it indented. Java doesn't care about indentation at all. You should still indent properly just to make your code more legible. If you have no indentation, like this code is just harder to read than code that's indented properly. But it won't have any syntactical meaning like it does in, oops, I'm hitting the wrong key combination. It doesn't have any syntactical meaning like it does in Python. Python takes indentation very seriously. That's how it knows when you start and end a code block. Java does that using braces. And that is one of the big things we'll start talking about today, especially when we get to the memory diagram of this code, is any pair of braces like this will define a code block. These do exist in Python, but you don't have to care about them as much. In Python, it's the indentation defines a code block. In Java, we do have to pay attention to these code blocks a bit more, and we'll see the difference when we get to the memory diagram. So else if, let's finish up our method here so we can get to the said memory diagram, equals 7. So if we're in the 70s, we want to see, but I want to do this a little bit differently. I can't even set this up the way I really want to, but that's fine. We're going to have some string answer equals C, and then return C. So I'm doing this just so I have a variable that's declared inside of a code block, because Java does handle this a little differently than Python does, and it's a whole new concept in the course that we need to start talking about. And else if 10's greater than equal to 6. And the logic of the conditional, it's behaving the same exact way as you would expect from any other language. So we're going to check the if condition. If this is true, run this code block and end the whole thing. If this is false, check the next else if. If that's false, check the next one and keep checking them until one of them's true. If none of them are true, we're going to fall into the else block. So else, return big ol' F. Now, one thing that is different in Java, another thing that's different, is this return type. Remember I said that the return type is a contract, and any path through your method must result in that a value of that type being returned. So any path. Now, for the examples on Tuesday, there was only one path through any of our methods. But now that we have conditionals, we have multiple paths through our code. We can hit any one of these code blocks for the conditional, and they all have to result in returning a string, or else we get in trouble. So every single one of them has to return a string, and they do in this case. But also, we need an else statement. If I don't have an else statement, then Java's going to say, well, what happens if this is false, this is false, this is false, and this is false? In that situation, there's a path through your code that does not return a string, so we can't do this. We can't proceed because you're not always returning a string. And that's what this error is on the closing brace. It's going to say, you told me you were going to return a string, and you didn't. Missing return statement. If we try to run this, I think it's a different error message if we try to run it. No, just missing return statement. I thought we'd get it was a different error message that comes up. But we don't have a return statement if all of the conditionals are false. So let's get our else back in there. Return F. Now the error goes away, and we can successfully run this code. We should say CACE build. How did I lose that? Or ACF, I mean. I'm going alphabetical instead of skipping E like we do. We see ACF, and that's the expected output of this program. So that's conditionals in Java, very much like conditionals in any other language. So let's take that and head over to the memory diagram and trace this thing. I want to close the tool. Trace practice. We're going to trash can all that, all my hard work. Oh, it's driving me nuts. Okay. Here we go. Let's just keep plugging along. And always, if there are questions, the first lecture didn't have questions. It actually, to the point where they had some questions, but it got to the point where I was worried that the stream was broken. So if you do have questions, make sure you're asking. I can stop to answer some questions. Always happy to do so. So let's do this every Java program. We've seen this enough times. I'm going to stop making a big deal of it, but every Java program starts with the main method. So that's a main stack frame. The main method call has a main stack frame. That's how every program starts. As opposed to Python, like if we switch to Python, we have the global variables that doesn't exist in Java. So when we switch to Java, that goes away. There are no global variables in Java. It doesn't exist. There's no global namespace. Okay, so this first line, this is the first time we're seeing this exact situation. Again, if you're from 115, this is all review, but just to make sure I'm covering everything, this is where we have a variable that's being declared and assigned in the same line. So we have this variable being initialized in the same line. So we have this variable. I gotta do an audio check. I want to figure out this audio crap. Oh my goodness. You gotta be kidding me. Since I installed Adobe, it had a notification that says, hey, I'm not your default PDF reader. Yeah, I don't want you to be. So when we have this situation, what we're going to do is actually create the variable on the stack before the method call. Technically, this isn't what the computer does. The computer will resolve the right-hand side first and then create the variable to store it. We do this a little backwards in our memory diagrams for one specific reason, is we have a method call that's going to create a stack frame with the name of the method that's being called. And when we do our return arrow, we need some place to put this return arrow, and that's going to be the variable where it's going to be returned. So we're going to create the variable on the stack with no value just so we can have that return arrow pointing to the place where it's going to be returned. So now we have this return arrow into grade, this variable that doesn't currently have a value, and then we can start calling our method. So letter has a parameter score, getting the value 98 for this first call. First line that's executed, tens equals score over 10. So we have a new variable tens, which is going to get the result of score, which is 98 divided by 10. Score is an int. 10, I just put 10, not 10.0, so that's an int. So this is going to be integer division. We're going to use our friend integer division for this one. So we would get 9.8. Since it's integer division, we just get 9, which is what we're going for here. We're trying to just get the tens digit out of this number, out of this input. And that's exactly what we got here. And these, just take a quick aside here, these examples, this and one of the Tuesday examples, are set up in a way to, I said this the wrong way in the other lecture too. I got to rephrase this carefully. Integer division is an important thing for you to know, and the sum of digits method on task 1 is designed to get you practice with integer division, and then it's covered in lecture to prepare you for that question, but really to prepare you for understanding this core concept of integers, this integer division idea, this concept. So the intended solution, and I'll give more hints at this once we have the full context, but the sum of digits can be pretty tricky if you don't know how to approach it. So I do get pretty heavy-handed with the hints here and basically tell you how to do that method, and that's up to you to learn Java syntax and implement it. But integer division is a very useful thing for that method. If you combine integer division with modulo 10, you can get each digit one at a time out of that method. So if you have a 3-digit number and you divide it by 10, you're effectively erasing the ones digit and shifting all the digits to the right by 1. So it can be a helpful thing in doing that part of the assignment. So, and again, I'll revisit that when we, at the latest Tuesday, or Tuesday I'll revisit it again. I might revisit it again today. So if 10's greater than or equal to 9, 10's is 9, so that's true. So right away we're just going to return 9. So cross this out, return 9. Done. And we're back in the main method. We're going to print out grade. Grade is 9. 9. On to the next line. Here we're not creating a new variable. When we are declaring a new variable, we specify the type. When we're reassigning the value of a variable, we just use the variable name itself. So we're just using the name. We're reassigning to the same variable in this method call. So letter is going to return to the existing grade variable. We have letter where score, the parameter is assigned the value of the argument, 74. Shouldn't it return the letter? Oh, good call. What am I doing? Thank you. Thank you for that. And now score is 74. We're going to create, maybe that's how I can make sure the stream's working, is I'll just make mistakes every once in a while, so y'all have to call me out. It's a terrible idea, but that did help, so I know the stream and chat's working. So 74 divided by 10, that's integer division again, so we get 7. Then we go through our conditionals. If 10's greater than or equal to 9, that's false, so we go to the else if. 10's greater than or equal to 8, that's false, so we go to the next else if. 10's greater than or equal to 7, that's true, so we're going to execute this code block and then skip the rest of the else statements. We're actually going to return C in this code block, but we would not check the next condition. We would not go to the else. We would be done with all the blocks in this conditional. So here we have our first code block that matters, dare I say. Our first code block that matters here. So whenever we have a variable that's declared inside of a code block, so your clue for that is there's a type and the variable name. So we're declaring a new variable inside a code block. That variable has to go inside of a code block in our memory diagrams. So I'm going to click this Create Code Block button, and that's going to give me this dashed box. This dashed box, I like to think of this as semi-permeable. When you're inside a code block, you can still cross over this line and access the variables outside of the code block, as opposed to the solid boxes for our stack frames that cannot be crossed under any conditions. We can never cross from one code block to another. but we can cross, or one stack frame to another, but we can cross code blocks, the dashed boxes. Whenever a variable is declared inside of a code block, we have to indicate that in our memory diagram to show that that variable was declared inside this block. The reason for that, which won't come up in this specific example, but it will come up later today, is when we hit the end of a code block, all of the variables that were declared inside of that block are destroyed and will cross out that code block to indicate that those variables are no longer in memory. In this case, we're actually going to return C right away, so it doesn't end up mattering. This is just the first time I want to show a code block in a memory diagram. We're going to return C, so the code block ends at the same time as the stack frame, and we're going to hit the correct button, and that's going to cross out A and replace it with the variable, the value C on this line. So grade equals the return value of letter of 74. It ended up returning C, so we put C over here. And by the way, this isn't something we would, that doesn't actually matter either way. But this isn't really something we would do. We would just do return C just like we did in the other ones. But the only reason I'm setting it up this way is to talk about code blocks for the first time. And it's the only reason I'm declaring that variable there, just to talk about code blocks. Okay, and then we move on to the next call. We have one more stack frame. Letter returns to grade. Oh, I didn't, man. What am I doing? I didn't print C to the screen. Letter is going to get the score of 3. Three divided by 10 is going to be 0. So tens, which we expect. The tens digit is 0. And when we divide by 10 to get the tens digit, we get 0. 0 greater than or equal to 9, false. 0 greater than or equal to 8, false. 0 greater than or equal to 7, false. 0 greater than or equal to 6, false. So we get all the way to our else block here. And we just return F. So cross this out, return F, get back to the main stack frame, print F to the screen. And we reach the end of the main method, cross out the main frame, the main stack frame. Cross out the main frame. Man, that audio. If I move the mic. I don't like it there. We'll try it though. Okay. So no questions on this one? Actually, I can just move this over. Maybe this ain't the worst thing. Okay, if you had time for questions, and you can always just, you're really low. Okay, I can turn that up. Is that better? I was thinking the gain was too high is why it was doing that, so if it's too low, let me know if this is better. Sir, set your mic. What could you possibly mean by set your mic? I have lots of settings with it that I've been playing with. It's if you know what settings I should be at, it'd be nice. It's good now? Okay, good. Okay. But hopefully that's not an ongoing issue. I hate having mic configuration issues. So the mic itself has 4 different settings, and it has the gain on the mic, and then I have the gain in OBS as well, and then filters that I can add. There's just a lot of options for it. Been playing with them all, and none of them, well, let's see. actually sounds pretty good right now. Yeah, it was. Yeah, and I don't know what was causing that bass boosted, but it sounded better now, so I'm rolling with it. Okay. I'll play with it offline and see if I can figure something out. I thought I had it figured out after the test stream, but I'm distracted by the mic stuff. So that's plus minus. Let me fix this one. That should be answer. And go on to loops if there are no more questions about this one. So let's do loops. And this is all going to be in a main method. And we want to talk about a couple of loops here. So I'm going to create int. What's up, BK Rana? Int, nope, double val equals 10.0. This one I'm going to deviate a little bit from the slides because there's a few things that I just want to talk about that I don't have set up in the slides. And then I want to use the big old while loop, which I think they do cover in 1.15 these days, so it's not as critical that I start from scratch here. But I want to do a while loop. A while loop is going to be very similar to a conditional. So I'm going to need some Boolean expression here. So while val greater than 1.0, oops, greater than 1 I want to do. While val greater than 1, I'm just going to print val to the screen. And I'm going to divide val by 2. So a few things to talk about here. Oh, and I want this to be 10. So a few things to talk about here. So a while loop, let's talk about the loop first because that's the core of this example. The syntax for a while loop in Java is the same as for Python, but just in case you haven't seen while loops before, this is the same syntax as a conditional. So while some Boolean expression, this is going to check if the Boolean expression is true, and if it is, it's going to execute the body of the loop. But what makes it different from an if statement is that once it gets to the end of the body, it will go back to the conditional and check it again. If it's still true, it's going to run it again, then check again, and keep running and checking until this condition is false. Once it's false, it goes to the end of the loop and continues with the program. So it's going to execute while this condition is true. It's going to keep executing the body of the loop. The rest of this, let's do this syntax first. So this divide by equals in 1.15, if you took it here, you probably saw plus equals. This is going to add 2 to the value val, which is the same as saying val equals val plus 2. So you should be used to that syntax. If not, you just learned something. Congratulations. Same thing with divide by equals. I'm going to divide val by 2. So this is the same as saying val equals val divided by 2. But going back to the expectations of the course, I expect that you want to learn about computer science since you sign up for a second course in computer science. I'm going to start showing more like tips and tricks things in lecture. I'm not going to hold back on too much stuff. There are some things that we simplify a little bit. But this is something where I'm going to show you more syntax like this. So val divide by equals. We could also do multiply by equals. We could do minus equals. All of these are valid operators. This is valid syntax that we can use in Java. The other thing I want to talk about is I'm using ints in every one of these cases. Like the difference between 10 and 10.0 we saw in the previous example. 10 is an int, 10.0 is a double. Please make one video about CSS. I'm not exactly taking requests. My name is Jesse. This is an actual course taught at a university. I make it public, so if you stumble upon the stream, you're welcome to join in. But not taking requests. I'm covering what the course is, which is second course in computer science taught in Java, which is covering mostly object-oriented programming and a few data structures, and also unit testing. Those are the topics you'll see from me. So val is a variable of type double, and it's being assigned a value that's an int. And with most cases, I say, oh, your types need to match. Your double can only ever store a double, which is true. And usually you have to always assign it a double. This is one case where that rule is bent just a little bit. If you have a variable of type double and you assign it an int, specifically an int being stored in a double, Java will auto-convert this int to a double for us. So we have the int 10, it's being assigned to a double, so Java will convert it to a double and then assign the double equivalent into the variable val. So so this is one case where we can be a little lax, and I do it 3 times here. I'm comparing a double to an int. That's allowed. The int is going to be converted to a double. I'm dividing a double by an int. The int is going to be converted to a double, and I can get away with all of those. If I have a method that takes a double and I give it an int, it's going to be auto-converted to a double. You can't do that the other way around. You can't take a double and store it in an int, because you would have loss of precision in that case. The decimal portion would be lost. But from an int to a double, you can take every possible integer value and stuff it into a double, and it's going to fit just fine. So you're not losing any precision that way. So it's perfectly okay to do that. And I want to just s out val just to get the final value. Let's even do final val. This I wanted to add. It's not in the slides. I want to add that one in there. The next style of loop is a for loop. You've seen for loops in Python, but not quite like this. So let's get our setup for a for loop. X equals 0, x less than, my goodness, I can't do that, 4, x plus plus. S out x. Okay. Let's do this. Now let's try to run this. It's going to give me an error here, but I want to talk about what this error is. Yeah, when I get an error, it gets rid of my face. Oh, because the build is breaking. So it comes up with the different, I see, and then that's replacing my face thing. Okay, so with this one, with a for loop, we have 3 separate statements to be able to control a for loop. And I'm going to start with the middle one here, this x less than 4, because this one behaves just like a while loop. So a for loop is kind of like a while loop with some extra functionality on top of it. So a for loop, when we get to the loop, we're going to check this condition, and as long as this condition is true, we're going to keep going around the loop just like we did with a while loop, except we have 2 other statements here that are controlling how this loop behaves. So the first one is the initialization statement. This int x equals 0 is being executed exactly 1 time when we first get to the loop. So when we first get to this loop, this is executed. And importantly, part of our big conversation about code blocks, even though it's outside of the braces physically, the initialization statement is executed as part of the code block for this loop. That means in our memory diagrams, that variable x is going to go inside the code block for this loop. Why that's important is once we hit the end of a code block, all the variables declared inside that code block are destroyed, which, by the way, is not how it worked in Python. That's why in 1.15 no one ever talked about code blocks, and you never put a code block in your memory diagrams. It's because they behave differently. In Java and in most languages, Python's the outlier here, your variables declared inside a code block are destroyed at the end of that code block. So when I hit the end of this code block, the variable x is going to be destroyed since it was created as part of the code block. So right here, I'm getting an error because I'm trying to print x to the screen, and it says can't resolve variable x, cannot find symbol variable x. X is no longer in memory because it was deleted as soon as we hit this closing brace. Once we hit that, that variable's gone. And when we try to print it out here, you get this error, which can be very frustrating if you don't know how your code blocks are working, because you're going to look at your variable X right here, and you're going to say, look, I'm declaring a variable X right here. I'm trying to print it right here. It's only a few lines away. How the hell, Java, can you not find my variable X? And it's because X got destroyed when the code block ended. And this is true even if we create like int y equals 70, and I try to print out y down here. I can't print out y either. I'm going to get the same error. Can't resolve symbol y because y was declared as part of this for loop. The block for the for loop ended. Y is erased, and I don't have access to y anymore. As opposed to val up here, which we can keep, this does work. Val was declared before the code block started. So when this while loop code block ended, there were no variables declared inside this code block. So that's why I didn't have to, I forgot to mention this on the other memory diagram. So that's why I didn't have to, that's why no variables were destroyed here, and I can still access val, because even though val is very much a part of this loop has everything to do with val. Since val was declared before the loop started, this variable was in the main stack frame, but not in the while loop code block, so it lives after that code block ends. But X was declared as part of this code block, so when the code block ends, X is gone, and Y in this example too. So let's clean up our errors there. We can run this to see what it's going to print. There it is. But more importantly, let's just go to the memory diagram and take a look at every single step of this program. The one thing I forgot to mention, this last call to letter, when we hit this code block and we just returned F, we didn't put this code block on the stack. And for the first call, we didn't put this code block on the stack either. We did hit a code block, but since we didn't declare any variables inside of the code block, there was nothing to do with it. There's nothing to add to that code block. So in those cases, we can just skip putting the code block in our traces entirely, and that's perfectly fine, just like I did here. If you want to put your optional code blocks in your memory diagrams, that's fine too. I'll give an example of that in this trace. So hide toolbar, full screen. Let's do some loops. So every trace starts with a main stack frame. We have val equals 10. We didn't start any code blocks yet. Technically we did. I forgot to mention this earlier too, but our code blocks are going to be associated with loops and conditionals. We do have code blocks that define methods also, but when we have our code block for a method, that code block is going to create a stack frame, so that's treated a bit differently when it's a method. And also we have a code block for our classes themselves, but this code block is a container for all of our code, and that's, again, treated differently. It's creating a class. It's the definition of a class, so we're not going to trace anything for that code block. So we have val. We aren't not in a code block yet, so val is going to be created in the main stack frame. The 10 integer is going to be converted to a 10.0 double, so I'm going to put 10.0 on the stack since val is a double. And by the way, in these traces, there's a lot of little things like that where it doesn't have anything to do with your learning objectives, your classes, inheritance, linked lists, and trees. So it's not a big deal. If you missed that one, if you put 10 here instead of 10.0, I honestly don't care, because it doesn't have to do with 116 learning objectives. So I don't care. But when I'm covering these memory diagrams in lecture, I will explain all the little details. I want to at least tell you what they all are. But if you make that mistake, 10 instead of 10.0 on your trace, it's not like you're going to get an F in the course immediately. Didn't complete all the learning objectives, fail on the quiz, and no, we don't play those games. Okay, so we get to the while loop, and we do start a code block. Now, I can look ahead at this code block and see that no variables are declared inside this code block, so we don't have to put the code block down. But you do have the option to. If you want to add all of your code blocks, I can still create the code block, delete the variable, and just have a code block with no variables in it. This is what we would have to do for all these code blocks. Is just have an empty code block there for our while loop. So whenever that's the case, whenever you would have a code block with no variables in it, you have the option of just not tracing the code block at all, which is perfectly acceptable, except for this one exception that I'm doing right now just for this example. Aside from this, I'm not going to trace my code blocks that don't have any variables declared in them. In your traces, if you want to trace all your code blocks, so whenever you hit an open brace, you hit a code block just so you don't forget about code blocks, and then you hit the closing brace and you cross it out. That's perfectly fine. If you submit your quizzes with empty code blocks, perfectly fine. Absolutely fine. What was I say? Oh, but if you don't have any of your empty code blocks, that's perfectly fine too, and that's what I'll do in lecture. Okay, so we hit our while loop. While val greater than 1, which is true, val has the value 10. So we're going to execute the code block. We're going to print val to the screen, so 10.0. And then val divided by equals 2. So we're going to take val equals val divided by 2, and this is going to get the value 5.0. Then we're going to hit the end of the code block, the end of the loop, the body of the loop. So we're going to go back up to... I didn't even finish explaining for loops. What the hell am I doing here? I guess I'll finish explaining for loops when we get to it. I didn't even talk about the increment statement. I got sidetracked with scoping, I guess. So once we hit the end of the body of the while loop, we're going to go back to the conditional and check the conditional again. Val greater than 1, 5.0 greater than 1 is still true. So we're going to execute the body again. We're going to print 5.0 to the screen. We're going to divide val by 2. And we're going to check the condition again. 2.5 greater than 1 is true. So we're going to go around again. We're going to print val, which is 2.5. 2.5, we're going to divide val by 2. 1.25. We're going to check the condition again. Val 1.25 greater than 1, that's true. So we're going to run it again. 1.25. Divide val by 2. 0.625. And then we're going to check the conditional we're going to check the conditional again. 0.625 greater than 1 is false. So we're not going to execute the loop body again, and we're going to move on with our program. So we broke out of the loop because the condition is now false. But notice that at the end of this loop, and there's a nuance point here, where at the end of the loop, the value for val is 0.625, but we never printed 0.625 to the screen. We never executed the body of the loop with with val having a value of 0.625. So this is something that comes out in the memory diagrams that you might not think about or notice or even care about when you're writing your code, but the value will reach a value that makes the condition false without running the loop with that value. So the last thing we print is 1.25, but the ending value for val is 0.625. And this is where students can get into a little bit of a trap, where you're overthinking the memory diagrams. If you're overthinking the trace, it's easy to make a mistake here, because what some students like to do is they get a little too clever, a little too smart, and they look at this loop and they say, okay, this loop, val starting at 10, it's going to divide by 2 each time this loop executes. Okay, so it looks like this loop's going to print 10, 5, 2, 1.25. Like, that's what it's going to do. And they'll, like, analyze everything and figure out what it's going to do. And then they'll go over to the stack. So they'll do all their IO lines. Then they'll go over to the stack and do 10, cross it out, type 5, cross it out, type 2.5, cross it out, type 1.25. But when they do this, they're usually not going to put the 0.625. When we're grading the trace, it's obvious that they didn't actually go through the loop because they missed the 0.625. Please, the way to avoid this is to just actually trace the code. Don't stop trying to shortcut things. When students try to shortcut things, then they make mistakes, then they fail quizzes, then they fail courses. If you're not trying to, and this is especially true when it comes to these traces, these tracing quizzes, let me answer this question first. So why did we not type 625 to the screen? So it's when we divided by 2, val became 625, but we didn't print. We're not printing to the screen yet. We're only printing to the screen if we execute the loop again. So when we hit the end of the loop, we're checking the condition again. And now the condition is false. We have 0.625 greater than 1. That's false. So we never execute this line when val has 0.625. But val has to reach 0.625 to make the condition false so we can break out of the loop. So when it becomes 0.625, we check the condition, which is false, and then we break out of the loop and go down here, which we will print 625 on this line right here. But we don't ever hit this line while val has the value 0.625 because we already had a condition of false, so we broke out of the loop. So the way to avoid making simple mistakes where you're missing the 0.625 is to actually trace through the code and go through every little step like I just did here, where we're not trying to take any shortcuts. Just trace through every single thing. Check the condition, memorize the rules of how loops work, how conditionals work, and then trace through every single step that's going to happen. Do exactly what the computer is going to do. The computer does not think at all. It just has a set of rules for the language that say when to check the conditionals, when to execute a line of code, etc. Follow those same exact rules and you'll always do great on these tracing quizzes. So we check the condition. If the condition is true, execute the body. When we get to the bottom, check the condition again. If you just go through those rules, you don't make any simple mistakes like that. You're always going to have exactly the right output for your trace. So do every single step. You have plenty of time on the quizzes. There's no reason to take shortcuts. Just go through every single step as intended, as the computer does. And then you'll never miss things like that. That said, on this specific example, that would definitely be a minor mistake. If you stopped at 1.25 right here and you never had the 0.625, again, it doesn't relate to the learning objectives of 116. It'd probably be a fail in 115 where loops is a learning objective. Tracing loops is a learning objective. In 116, I ain't as concerned. Yeah, no problem, Jessamar. Okay, now let's continue with the program. So next we print to the screen final value of val. Final val is 0.625. So we will print it out here just to emphasize that point. So when we're in IntelliJ, we can see that the output matches exactly what we're tracing here. So val reaches 0.625, but we never execute the loop body with val being 0.625. Let's get to the for loop. Let's finish explaining what a damn for loop is. Oh, sorry, I missed one thing. Because I usually don't do my empty code blocks here, so I forgot this. But when we hit the end of a code block, we cross it out. Any variables in that code block are destroyed. There's no variables in this code block right here. Val was declared in the main stack frame, not in any code blocks inside that stack frame. So val survives the end of this loop, and that's why we're able to access val still. Val's still in memory because it wasn't declared in this code block. Okay, for loops. So the initialization statement we execute exactly one time when we first get to the loop. So that's going to be what we execute right now. Let me trace it while I'm explaining it too. So we have a new code block for the loop. We have a new code block, and the initialization statement is executed as part of the code block of the for loop. It's one of the kind of exceptions. It's physically outside of the braces, but it is still part of the loop. So x equals 0 is part of this for loop. The for loop's going to execute as long as this condition is true. And each time we execute the body of the loop and get to the end, we don't just go right back to the conditional like we did with a while loop. What we're going to do is execute the increment statement first. We're going to execute the increment statement and then check the conditional. So this x plus plus, this is some new, another new piece of syntax. X plus plus, semicolon, is the same as x plus equals 1, which is the same as x equals x plus 1. So x plus plus is a shortcut to say increment this value by 1. So that's what x plus plus. There's also x minus minus for what it's worth if you want to decrement by 1. There's also plus plus x and minus minus x. There's all these. All of those exist. But it means x plus plus means x equals x plus 1. Okay, so we get to this loop. We run the initialization statement exactly one time. And then we check our condition. X less than 4, x 0 is less than 4, so that's true. So we're going to execute the code block for this, the body of this loop, which is just going to print x to the screen, which is 0. Once we get to the end of the body of the loop, we're going to execute the increment statement. So we're incrementing x by 1, and then checking the conditional again. 1 less than 4 is true, so we're going to go around the loop again. We're going to print x to the screen. X has the value 1. Then we're going to run the increment statement. X gets the value 2. 2 less than 4 is still true, so we're going to execute the body of the loop and print 2 to the screen. Hit the end of the loop. We're going to increment x. And again, go step by step. I know when it's a loop, it gets a little tedious sometimes, but just go step by step. You're never going to forget anything because there's nothing to forget. You're just blindly going through the steps the same way the computer does. 3 less than 4 is true, so we're going to execute again. We're going to print 3 to the screen. Get to the end of the loop. Run the increment statement, which is bumps us up to 4. Check the conditional. 4 less than 4 is false. So now we do not execute the loop again. We go to the end of the loop and continue with our program. And we cross out the stack frame, meaning that all the variables, the code block, that means all the variables in that code block are destroyed, which is why x is no longer in memory after that loop ends. So now that the loop is over, x doesn't exist anymore. So that's why when we tried to print x down here, there's no x in this stack frame. There's no x existing because it was in this code block and it's gone. Val still exists. We can still mess around with val. We can't mess around with x anymore because it is gone. And also notice that x did the same thing val did. X reached the value 4, but we did not print 4 to the screen because as soon as x was 4, the condition was false. So we never executed the body of the loop with the value of x equals 4, because that value, as soon as we incremented to 4, the next thing we did was break out of the loop because the condition was now false. Could you write that loop as a while loop as well, like how you did in the earlier example? Sure. Yeah, and I actually want to go back to right, we're done with this example. We reached the end of main, cross out main. Let's do that right now. If I can get the right keyboard shortcuts here. So I can actually change this to a while if I wanted to, which I do want to because it was asked. So I'll be happy to. So first, before I change it all the way to a while, one thing to note is that the initialization statement can be empty. We don't have to have something there. We have to have this semicolon to say, hey, Java, I'm done with the initialization statement, even if it's no code at all. Even if nothing happens, we still have the semicolon to say, I don't want an initialization statement. So we can declare x before the loop. Now x would be created outside of the code block for the loop. And in this case, I can actually do s out x. X is going to survive the loop. And then we can actually see, just to avoid confusion, let me do final x. just to show that that's not being printed as part of the loop, it's printed after the loop. So final x is 4. We can verify that what we did in the memory diagram is what's actually happening when this code runs. We print out 0 through 3, but the final value of x is 4. We print out 10, 5, 2.5, 1.25, but the final value of val is actually 0625. So everything's matching what we did in the trace, so we're feeling good about that. Feeling like we got the right things going on. So we can initialize beforehand, and same thing with the increment statement. The increment statement is optional. You still have to have the semicolon here, but we can get rid of that. And since the increment statement is always the last thing that happens, like right when we hit the end of the body of the loop, I can just put that increment statement at the end of the loop. And now the warning that I'm getting here is, hey, your for loop really looks like a while loop. You could just use a while loop here. And then I would do while. Get rid of my semicolons because while only takes one expression, a Boolean expression. And now I've converted my for loop into a while loop. So if you say, you know what, I don't want to ever use for loops, I'm going to use while loops for everything, that's perfectly fine. And vice versa. If you have a while loop and you want it to be a for loop, you can add your semicolons here and just make it a for loop. There's no reason to do that besides preference. But if you do have that preference, let's get this back to where it was. But if you do have that preference, you can convert one loop to another. It's a little different. When we converted this for loop to a while loop, that it was actually a little different because x was outside of the scope. So if you do want x to be destroyed with this for loop, which we'll see in the next example that sometime, or 2 examples from now, sometimes we actually do want to do. So we can reuse that variable name is the main reason, and it doesn't clutter up the stack, I guess. If we're worried about memory usage, usually we're not, but in 2025 we have so much memory. An extra int or 2 isn't going to make a difference. But if you're doing like embedded programming, sometimes it does. So so there is a difference there with the while loop. You are a little less memory efficient. So something to keep in mind, at least way down the road, not in 116. We don't care about that in 116. But down the road, you might. So that's the question I already answered. And we're ready for the next example. Right? That's everything I want to say. Actually, I do want to go to slides right now. As much as I say I don't want to do any slides in the 11 a.m., there's a brief moment right here where I want to cover a couple of slides, which I should actually have open already. 2-1. Learn all my keyboard shortcuts here. Because there's I think twice in the whole semester, I think there are 2 things where I just don't really know how to talk about this without slides. I mean, I could, but I don't know. Just to have this image on the screen is nice to have. But I want to talk about what memory is. It's like 4 slides. 4 slides just talking about what memory is, and then we'll go back to live coding. So I want to talk about what memory is, and hopefully they talked about this in 115. I really hope they do, and someday I'll ask them and check, but if they talk about this. If not, or even if they do, it's a good reminder. I want to make the connection between what we're doing in the memory diagrams to what it's representing in the real world. So let's just zoom out a little bit and talk about what we're even messing around with these memory diagrams. I moved this mic, but now I can't see the clock. 12:03. Okay. Doing good on time, actually. So let's talk about it. So what we mean by memory is random access memory, your RAM sticks. You all know what memory is from the side of purchasing a device when you're shopping for laptops or desktops. One of the big specs that you're looking at is how much memory does it have? How many gigs of RAM do I have in this new machine? And that's exactly what we're talking about when we're talking about stack and heap memory in our memory diagrams, in our traces. I'll call them memory diagrams and traces kind of interchangeably, by the way, or memory traces. If I say the words memory or trace, I mean what you're doing on your quizzes. That's what I mean by them. But when we say memory, we actually mean the memory in your machine. And if you ever built a PC, you know it's these RAM sticks. These are the sticks of RAM, of memory. And these are effectively a giant array of bytes. This is a big array indexed at 0, except we can't, it doesn't matter. Let's not get down a rabbit hole. But index is 0, and then each index is a memory address. And that memory address is the location for a specific byte of memory. And then our values are stored across multiple addresses, like a double is a 64-bit value, so we need 8 memory addresses to be able to reference that. Usually when we store it, we only have the reference to the first byte of memory, and then we know it's a double, so it's going to be that byte and the next 7. But that's what it is a giant array of bytes. And this is where all the everything is stored for our computer, for our machines, for our programs, I mean. All of our, everything in the stack, all of our stack frames, all of our variables, everything that's on the heap, which we're going to start talking about today, all of it goes into this, into that RAM. That's where all of our stuff goes. It's like the working memory of a program, of a computer. And our programs, I guess, both are true. So when we start our program, the first thing we need to do is get some stack memory. So we're going to go to the operating system. We start our program, and our program is going to go to the operating system and say, hey, I'm ready to run. Operating system, I'm going to need some memory for my stack. And I'm going to say operating system in these few slides. In Java, it's actually going to the JVM, which goes to the operating system, so we have an intermediary. But in general, in every programming language, eventually something has to talk to the operating system to be able to get memory allocated to that program. So I'll say operating system in these when I'm talking at this level, because that's going to translate to any programming language, anything you're using. So we go to the operating system, we say, hey, I'm about to run. I need some memory. And the operating system says, okay, I'm going to find some memory for you for your stack and give you this chunk of memory. And that's what we get. That is what it is. Whatever memory the operating system gives us, that's what we're allowed to use for our stack, because the byte before the start of that chunk of memory might be used by another program, and the byte after might be used by another program. We have to stay within these confines, and if we use too much memory, too much stack memory, our program blows up and we get a stack overflow error. Now, the amount of memory that we get for the stack is pretty large. In most cases, you're never going to have to worry about running out of stack memory. But it is possible. We'll see it. Oh, that's Tuesday, actually. We will actually see a stack overflow error on Tuesday, but we have to create that by going infinite, and infinite is not a finite number, so it doesn't matter how much stack space the OS gave us. We're going to blow it up. We're going to blow it up on purpose on Monday. And then the program just crashes at that point. So that's the only space that we have. So we have our own personal chunk of that RAM stick that we're allowed to use for our stack. And the stack is one continuous chunk of memory. All the values have to be exactly in order with no gaps in the stack. And this follows a last in, first out structure. And the stack really is a stack of stack frames. We have our stack frames, our main stack frame at the bottom. Visually, it's on the top of our traces, but it's on the bottom of the stack conceptually. And then whenever we call a method, it goes on top of that stack frame, and that method calls another method, which calls another method. They're all going to stack up. And the stack frame that's on the top of the stack, that's the only stack frame that's active at that time. And as long as that stack frame's on the stack, it's the only one that has access to anything, and it can only access the variables inside itself, its stack frame. And then if it calls another method, now it's not active anymore. But once this stack frame returns and is destroyed, then it's this stack frame that was underneath it is now in control of the program again. Once it returns what was underneath it, it has control of the program again, and so on and so forth until the main stack frame is popped off the stack. then the program's over. The stack's empty. So it really is a stack of stack frames. When we get to the linked list lecture, I'll talk about the stack data structure in a little more depth, and we'll build one out of a linked list. And when we get to that, I'll flash back to this and say, hey, remember when I said the stack is a stack of stack frames? I'll draw the connection again right here. And sometimes the stack just doesn't do it for us. And specifically, this is going to be whenever we have any objects. We're going to start talking about objects today. Those objects can't be stored on the stack because they're a bit too dynamic and sometimes just too big. And our first ones are going to be array lists and hash maps, which in 115 you saw lists and dictionaries. They were on the heap. Those were objects. They were on the heap and they were stored by reference. So heap space or heap memory, I sometimes say heap space interchangeably with heap memory, the heap. The heap is more dynamic. This is when your program is already running. The operating system already gave you your stack space, and as the program's running, your program is like, hey, operating system, I'm going to need more space over here. I need an array list of 1 million elements, and that's just not going to fit in my stack, and you wouldn't put an array list in the stack anyway, for reasons that we don't need to get into right now. But we ask for more space while the program is running. The operating system is going to go somewhere in RAM. It could go absolutely anywhere. And we don't know, we don't care where we get some RAM. But when the operating system gets that memory for us, because what we're going to do is, okay, we need an array list. Our program's going to say, okay, that array list is going to take up 100 bytes of memory. It's going to go to the operating system and say, hey, operating system, I'm going to need space in the heap for 100 bytes. And the operating system is going to say, okay, I found 100 bytes for you somewhere over here, wherever they found it, and return to us the memory address, so the index of the first byte of the memory that it allocated for us. It's going to say, here's the first byte of memory, and you have also the next 100 bytes, the next 99 indices. Also, they all belong to you. Don't go outside that area, but those 100 bytes, they belong to you, and here's the index of the first byte of memory. That index is the reference, what we'll say is the reference to that object. And we don't care where it is. All we care about is that we get that reference, which is our roadmap that says this is where you can find that memory. And then any variables that we think of as storing objects actually only store a reference to a location on the heap by memory address. That's what it actually stores. All right, so that's memory. And then when we get to array lists, I want to do this back in our usual 11 a.m. style. But just the background, I'm sure they cover that at least at some level in 115. Just the overview of what these memory diagrams even are. But as a reminder or whatever, I like to talk about that still. Array list example. Okay, main method. Let's create an array list. Array list. Some of this I just got to get the code out here, and then I get to call the variables something more meaningful. I don't like the variable names we use in the slides. There we go. It's fine. Yeah, and let's talk about this line for a long time. So I'm creating a variable of type array list of integer and assigning a new array list, and I imported array list. So that's the code we got to talk about, and there's a lot going on here. So let's do it. Let's start right at the variable type. So we know every variable needs a type. If we're creating an array list, which array list is like our list in Python, this is your array in JavaScript. It's your vector in C++, and it's similar to plain arrays in any language, but behaves more like the first three that I mentioned. So ArrayList is our sequential data structure that stores values at indices starting at 0. No matter what language you've learned from, whatever language you cover, whatever language you know, you've had this data structure in one form or another, where you have your indices starting at 0 up to the length of the size of the data structure minus 1. You've seen this data structure before. So in Java, we're going to use ArrayList as that data structure. And let's talk about this Java-specific syntax. So the point of that, I'll assume that you... Let's get rid of this. So I'll assume that you know how this thing behaves and kind of what the goal is of what we're doing here. And I got to talk about the Java-specific syntax, of which there is a lot. There's a lot of Java-specific syntax. And actually, I lied. We're not going to start at the variable type. We're going to start at the import statement. Last time I said there are two things that can go outside of a class. All our code has to be inside a class, except two things: package declaration and import statements. This is our first import statement. These will go outside classes. With Java, there are certain classes that are auto-imported, like the string class, which we haven't really seen before, but string is a class. There's a class that defines what strings are. Just like we're writing classes to store our code, there's a class. Oops, that's the wrong one. Let's close others. So just this one's open. There's a class that defines the string class. But when we use the string, we didn't have to import it. Same like system. Print out my list here. Same with system. This is a class. We can tell because it starts with a capital S. But we didn't have to import system either. Same with int. When we had int x equals 0, we didn't have to import int. Just a lot of things we didn't have to import. So there are a lot of things that are automatically imported in Java. The things that are so fundamental that the developers of Java said, you know what, everybody uses these things. Let's not make them import strings, because like everybody's going to use a string in every program ever. ArrayList, not so much. I mean, ArrayList is pretty ubiquitous, but not everybody's going to use an ArrayList in every program. So ArrayList is not auto-imported, because importing a class, it has the class loader load up the definition of this class into your program. If every part of the JDK was auto-imported, every program, even Hello World, would have quite a bit of bloat in it, because you'd have to load up everything, every class in the Java library. That's a lot of stuff, and that's really going to slow down our programs. So anything extra that you need is going to have to be imported, including ArrayList. And ArrayList, we import using, or all classes, all imports, we import using this syntax. Import java.util.ArrayList in this case. This is the fully qualified name of the class, which starts with the package name. So this lives in a package named Java, in a sub-package named util, in a class named ArrayList. So it lives in a file named ArrayList.java. And this is where knowing the naming convention and having Java enforce the naming convention can come in handy, because I know exactly where to find this code. If you want to look at the ArrayList class, first I'm just doing control-click on it to go to the definition. But I know exactly where I am with this definition. It's going to be in the JDK. Let's collapse Lang. It's going to be in its root directory, which we call source in our code. They call it java.base in this package, in this library. And then in a package named Java, and then a package named util, and then a file named ArrayList.java. So in the ArrayList file in that package, I'm going to find the ArrayList class, which has all kinds of goodies in it. We're not going to go through the ArrayList class, not today at least. And that's how I import it. So I'm importing that entire class definition into my code, and now I get to use the ArrayList class. If I do not import it, I'm going to get errors on my ArrayList, and it's going to say, you probably want to import that. So make sure you have your imports, but if you don't, IntelliJ is going to flag you down and say, hey, y'all got to import that. Now that it's imported, we get to use it. So now let's go to the type of the variable. We know all variables need types in Java. Let me get rid of this x equals 0 too. We know all variables need types in Java. So we need a type, and we expect that type to be array list. But we got a little bit extra here. We don't have just array list. We have array list and then angle brackets and then this integer thing. So let's talk about this integer thing. So you cannot create just an array list in Java. It's not allowed. Java is strongly typed and it takes strong typing pretty seriously, including as the types of data structures. So you can't just create an array list. You have to create an array list of some type. So array list takes a type parameter, and you have to specify what type this array list is going to be able to store. So I'm going to say this is an array list of integer, which means I can add integers to this list, and the add method is going to add values to it. So I can add integers to this, but I cannot add anything else. I can't add other types. So this array list of integers can only ever store integers. It cannot store our other types. Let's do 4. I can't store our other types. So I can't put a double in there. I can't put a string in there. It's not going to work for me. That's just not allowed. So you do have to specify the type of the data structure, not just that it is the data structure. So I'm creating an array list of integers is the way we would read this, and this array list can only ever store integers. So we do that with this angle bracket notation, and then on the right hand side we see the keyword new. Whenever we're creating an object on the heap, whenever we need space allocated on the heap for an object, we're going to use the keyword new. And what follows the keyword new is a call to a special method called a constructor. We're going to worry about what constructors are in a week from now. Next Thursday, we'll talk all about it. For now, you just have to know that it is a method call. So you will have a parameter list. Since you're calling a method, you have to give it its parameters. This parameter list is empty, so the argument list is empty, but you do still have to have your parentheses. New has to call a method, so we do have to have an argument list, even if it's empty. We also have to specify the type parameter on the right-hand side as well. So we have to have these angle brackets for the type parameter list, but Java does have our backs here, is it doesn't make us type integer again. This is correct. This is fine. This is the same code that we had. But you notice integer here is grayed out. And it says, hey, I know it's integer because you told me on the left-hand side that this is integer. So I know this is an array list of integers already. You don't have to tell me twice. So we don't have to put integer here. We can just put an empty type parameter list, and it's inferred from the left-hand side. So one way Java does reduce our typing a little bit, that we don't have to type integer twice in a line like this. And after all that, we finally get my list, which stores a reference to an array list on the heap. The heap stuff and the reference stuff, I'll save the deeper conversation for the memory diagram. And there's more. There's a lot to talk about on this one line. Integer. Notice that this is integer, not int. Int is an error. When I have a data structure and I have to specify the type of the data structure, it cannot be a primitive. So our int, just do that, double Boolean, which are the three primitive types that we've seen. We can't use any of these three as the type parameter for our types. We have to use our, let me just put this in comments maybe. Never mind. We can't use any of these three. We have to use class types. class types are any types that start with a capital letter. So string is fine. For what it's worth, array list is fine. Those are the only two class types we've seen so far. Array list is fine. Technically system is fine, but that doesn't make any sense. I don't know why you would ever do that, but it's allowed. Math. I shouldn't even type these because that's just confusing. Math would be fine. But the one that we have for this example is integer. So you have to have a class type. It has to be a capital I, a capital letter for your type. Not our primitive types, which behave different. The difference between these is primitive types are being stored by value. So when you have an int x equals 7, let's say, the value of 7 is stored directly in the variable x by value. The value is stored there. Whenever it's a class type, it's a reference that's stored in that variable. When you create a data structure, it has to be something that's stored by reference. So a few implications here. There's a big conversation here, but let's get it over with. Let's get all this out there. Integer is just like int, except it's a class type. So there's actually an integer class. So I have class integer, and it's a full regular class filled with goodies and all kinds of stuff. It's not just a value 7. This is just a 32-bit value, a binary value that stores the value 7. That's it. Integer is a reference to an object on the heap that has all kinds of methods. We can have dot operators and method calls and stuff on this thing. There's a lot we can do with it. We also have double. It'll be fine, and we can see we get this 4.8 just fine, but now the 5 is an error. I didn't point that out with string. String is only going to store strings, so now this one's fine, but the other two are, of course, not. And we can do Boolean. So capital B Boolean, capital D double. These are our class type equivalents for the primitive types. So Java gives us class type equivalents for each primitive type, and those are the ones that we have to use when we're creating data structures where we want to store ints or doubles or booleans. We're going to use their class equivalent types. And in most cases, Java is good about auto-converting between capital I integer and lowercase I int, lowercase d double and capital D double, lowercase b boolean and capital B boolean. Usually it's really good at converting between those. Sometimes it's not. And one time where we do get into trouble with that is when it's the return type of a method or a parameter type of a method. Specifically when you submit to Autolab, the way the Autolab testing is set up. So here's your rule of thumb to avoid any issues with that, is we're always going to use the primitive types. Always lowercase I int, lowercase d double, lowercase b boolean. Always, unless it's a type parameter for a data structure. That's the only time you're ever going to see me use these class type equivalents. That's the only time ever. Every other place, it's going to be the primitive values. So when a homework assignment tells you to write a method that returns an int, that method returns an int, not an integer, not the capital I integer. If you return the capital I integer, it's going to be errors in Autolab, and it's a really frustrating thing. You can waste hours trying to figure out what's going on, why you keep getting errors in Autolab. You come to office hours, and then in like 0.2 seconds, I say, well, you got capital I integer there. What are you doing? That's not what the homework handout says. I gave this big speech and lecture about it. Like, why are you even doing that? Sometimes it's a mistake, but I do wonder why anybody ever does that when there's nothing from the course that indicates that you should ever do that. A lot of students do. I have my suspicions of what's going on there, but I'll save that for another day. So don't do that. Save yourself some time. Don't make that mistake. Always use the primitive types unless it's a type parameter, or just follow what the handouts say. The handouts will never say return a capital D double. They'll just say lowercase d double, and then follow what the assignment says. Okay. So we got all that. Whoo, man. All right. This line always takes forever. I kind of dread that every semester because it takes forever to explain that one line. Where in Python it's this, and then we're done. Oh yeah, we're creating a list. Okay, let's start using this list. In Java, okay, imports, type parameters, difference between primitives and class types. I didn't say the word autoboxing. Autoboxing is a thing. So the fact that Java converts between like int and integer automatically, it's called autoboxing. It's a neat thing. But yeah, all that's over. Constructor calls, this empty type parameter list. There's just so much there. But now we're ready to actually use the thing, so let's do it. So I want to say for int I equals 0, I less than 4, I plus plus. So let's set up a for loop the way we did in the previous examples. And then I'm going to use our first list operation, our first array list operation. And array list, we do not have this syntax. Like in Python, you could do something like this, equals 5 or whatever. We don't have that available to us. It does not exist with array lists. Can't use that syntax at all. Instead, we're going to use .add if we want to insert a value into this array list. And what I want to add is 10 minus I, because that's what I do in the slides. So we're going to add some values into this array list. We're going to print that array list to the screen. And then we're going to write a method that takes an array list, and we're going to call that thing. So public static, what is this? An array list of integers, int. So I'm going to write a method that returns an int. So I'm going to use the primitive type. If it's a method that returns an int, I'm going to use the primitive type every time. Part of that's my preference. But part of that's to make it easier in the class. Like you don't have to think about what types to use. Always, always, always use the primitive types. And if it's a type parameter, that's the only time you're going to use the class types. But if you just always, always, always use the primitive types, and then if you get an error like this, you go, oh, wait. Type argument cannot be of a primitive type. Oh, I must have to use the class type. And then change it to a class type. If that's the way you approach it, you're never going to make that specific mistake that I see so many times every semester. I'm frustrated seeing it. It's something that you have to learn, but it's always frustrating. I get frustrated for the student, not at the student every time, because I have to see the pain like when I fix it in 2 seconds and they're like, oh my god, I spent hours on this and that was the issue the whole time. I don't like seeing that. I want to see y'all succeeding and completing the assignments without having to deal with extra frustration. So it's a frustrating thing. That's why I spend a lot of time in lecture right now talking about it. But return int, not integer. Every method is always going to be int, not integer. Lowercase d double, not capital D double, unless it's the type parameter of a data structure. It's the only exception. And let's call this sum. And I just want to add up the values in an array list of integers. So array list of integer, that's a type parameter, so I have to use capital I integer. If I don't remember that, if you don't want to memorize that, just type int, check the error message. This can't be primitive. Okay, if it can't be primitive, I only have one other option. Must be integer. And I want to call this my list. Because I want to reuse a variable name just to... Do I want to reuse a variable name? Let me call it list param. Then for... Oh, we didn't do that yet. For int I equals 0. So I'm going to iterate I starting at 0. I less than list param dot size. So I'm going to iterate over all the indices of this data structure. If you set up your for loop like this, start at 0, go while I is strictly less than the size of the list. So that means I will eventually be the size of the list, but we will not execute the loop at that size. So I and increment I once each time. So I is going to go from 0, and the body of the loop is executed from I equals 0 to I equals the size minus 1, which is exactly the indices of this list, of any list. And I got to set up my accumulator variable. So I'm setting up the accumulator pattern here. I want int, call it answer, equals 0. It's going to be my accumulator. Answer plus equals list param dot get. So this is the other method. If we want to get the value at a specific index, we're going to do dot get and get the value at I, then return answer. What's the warning here? For loop can be replaced with an enhanced for. Yeah. That's why I paused for a second. I'm like, no, we didn't do enhanced for yet. I can't use it yet. So this should come up with the sum of all the values in this list. And one more thing I want to do down here, I'm going to create a second variable, array list of integer my list. I'm going to have the very creative name of my list 2 equals my list. I'm going to print out my list 2. I'm going to have int result equals sum of my list 2, and then print out the result. So just get some code down here to run, and let's run this just so you can see what the output is. You can kind of guess what it would do, and then see the result here. But more importantly, we're going to jump to the memory diagram. This warning should say, why are you even doing this? This is dumb. Because it is a dumb thing to do. I like that there's a warning there. So let's jump to the memory diagram and see exactly how this code runs and what it does. So let's trash can this, hide the toolbar, full screen, paste. Get rid of some new lines here so we can see the whole code. Yeah, we only need 3 IO lines. Are we getting a hash map today? Hell yeah, we're getting a hash map today. Let's trace this thing and then get to hash map and finish up hash map. All right, so every Java program starts with main. We're going to create this array list, my list variable, my list. And whenever we see the keyword new, that's a new object on the heap. So this is our first object on the heap that we're creating. So a few things that happen. We see new object on the heap. We're going to specify the type of that object, which is array list. And we usually skip the type parameter. If you want to put the type parameter here, that's fine, but we just want to know that it is an array list. And it doesn't have anything in it yet. When we create an object on the heap, the most important thing to know is its reference. This is how we're going to keep track of this object. And when we say new and then a constructor call, this resolves to the reference of that object that was created. And that's what's going to be stored in my list. So my list gets the value OX100, which we're using as a memory address. That's the memory address or the index of the first byte of this object, of the data for this object. That's somewhere in the heap. We don't really care where it is. We don't know where it is. And when we actually run our programs, we'll get some randomish value, some randomish location on the heap for our objects. The memory tracing tool, this UB power, is always going to start at OX100, then OX200, OX300. It's going to do your objects in that order. But the numbers are arbitrary, and you can actually change these if you want. You can change this to 947. It doesn't matter what this value is as long as you are consistent. because no programmer has ever cared where in memory their values, their objects are, as long as they're consistent. I know my list, this variable, is going to store the location of this object that I created. That's what I care about. But there will actually be a specific location in memory. I'm going to change this back to 100 just to limit confusion. I just care that I know where that object is. I don't actually care where it is. I just care that I have my instructions. And this reference, that's my instructions of where to find that object. I like to think of this as my roadmap. This is the map that tells me where to find that object. OX100, that's where I can find my array list. That's the only thing that's stored in this variable. This variable, we like to think of it as Thanks, Alexa. So we can think of this as storing an array list of integers, kind of like answer we think of, because it is actually storing an int, because ints are stored by value. It's that answer is actually storing the value of the int. So you might think, oh, my list stores an array list of integers. It does not. It does not. It stores a reference to an array list of integers. It's kind of a nuanced point, but a very important one to understand. It stores a reference to an array list that's somewhere in the heap. It just stores the instructions of where to find the object. It does not store the object itself. Okay, so let's get on to our loop. This is a code block where I is being declared inside of the code block. We just saw that a few times. 0 less than 4 is true, so we're going to execute this line of code. And we're going to see our first dot operator of this semester, first of many, many, many. So my list, this expression, my list, is going to resolve to the value of that variable, just like any other variable usage like this. It's going to resolve to the value of the variable, and the value of that variable is OX100, which is a reference. The dot operator says, look it, I know you're a reference. Whatever is to the left of me, I know that resolved to a reference, and I don't care about references. Nobody cares about references. When we're coding, we don't care what the value of the reference was. There's no code you're ever going to write that says, depending on what the reference value is of my, we just don't care. We don't care what those values are. They're effectively arbitrary to us. The dot operator takes this and says, yeah, we don't care. So it says, I don't care what your reference is, but I do care. What I really care about, I care about deeply, is the object to which you refer. So the dot operator says, hey, reference, take me to your object. So whenever you see a dot operator, that's saying, okay, I know what I have is a reference. Take me to your object. So that dot operator takes us from the stack over to the heap to the object matching that reference. And now after that dot operator, we are over at this object right here. And then we're going to call the add method on this array list here. So we're adding to this array list at OX100. The value we're going to add, we have to resolve the argument here. This is a new expression, so we're no longer at the array list. We start over at the stack for every new expression that we're evaluating. So this expression 10 minus I is evaluated from the main stack frame, and I is 0. So we're going to add 10 to my list. When you add to an array list, it's going to add to the next available index. We have an empty array list, so the next available index is 0. We're going to add a variable with name 0 to indicate, array lists are just a little weird. We're going to pretend that name and value are index and value. We're going to add 0 and the value 10 at index 0. We hit the end of the loop, so we're going to run our increment statement. X goes up to 1. 1 is less than 4. That's true, so we're going to execute the loop again. MyList.add 10 minus 1. So at index 1, the next available index, we're going to get the value 9. I++. 2 less than 4 is true. Run it again. MyList.add 8. We increment again. 3. 3 less than 4 is true, so we execute again. 10 minus 3 is 7. The next available index is 3. Get the value 7. End of the body again. Increment I to 4. 4 less than 4 is false, so we break out of the loop and we go down here. So x got to the value 4, but we didn't add 10 minus 4 to the array list, just like our previous examples. Then we're going to print my list to the screen. When you print an array list to the screen, for what it's worth, the syntax is all the values separated by commas and square brackets surrounding them. So it'll be this syntax. That's one of those things, if you don't memorize the syntax of how an array list is printed to the screen, like, I don't care. If you put angle brackets instead of square brackets here, it has nothing to do with the learning objectives of 116. In 115, maybe I'd care. I'd probably care a bit more. 116, the assumption is that you've already learned that in 116. So if you make a mistake here, it was a simple mistake. You just had a momentary lapse of judgment or something. That's the assumption. Might be true, might be false, but that's the assumption. Then we're creating another variable, mylist2. Oh, we hit the end of the 4, so this is crossed out. I no longer exists at all. Creating a new variable, mylist2. And now we have a question. What happens right here? Mylist2 equals mylist. So if you're not thinking about it too well, I can't even say that. If you don't remember 115, I guess, you might be tempted to say that this is going to create a new object on the heap or something. I don't know. There's a lot of weird things that students will do when they get to a line like this. By the way, a line like this will, you can guarantee, show up on your every OOP trace. You're going to see a line like this. It won't necessarily be array list, but it'll be some object type, something that's stored by reference equals another thing that's stored by reference. Will happen. I will assess you on that because it's very important to know how this works. So mylist2 equals mylist. Treat this, if you treat this just like any other assignment, you're going to do good for yourself. So mylist, we resolve this to a value. What's the value of mylist? Well, the variable mylist has a value OX100, so this resolves to the reference OX100, end of story. Mylist2 gets that value OX100. And that's it. That's that entire line. That's all that happens. So a few little kind of cheat sheet tips is, since we don't see the keyword new, like last time I said, when we see the keyword new, we're creating a new object on the heap. The opposite is also true. If you don't see the keyword new, we're not creating a new object on the heap. Since you don't see the keyword new here, we're not creating any new object on the heap. We're not making a copy of this array list. We're not creating a new array list. We're not really doing anything. We're storing that reference to this array list, the map of where to find it in mylist2. So what in the end result here is that mylist and mylist2 both store a reference to a single array list. They are both referring to the same array list on the heap. And this won't come up in this example, but if one of these variables made a change to the array list, we would see that change in both array lists. Both lists would change because there is only one list and both variables are referring to the same list. Where if you're just looking at the code and not the memory diagram, you might think that there are two array lists and you might get really strange, confusing behavior if you're not understanding this. But seeing the memory diagram, we see that both of them store the same value, which is a reference, which refers to the same singular array list on the heap. So when we print out mylist2, it's the same list. We're going to get the same exact thing when we print mylist2 to the screen. And then we're going to take the sum of mylist2. So we have sum, we have result. We have a stack frame sum. We have it returning into result. We have a parameter list param, because it's a list and it's a parameter, and mylist2. So mylist2 is the argument, so we have to resolve that expression. Mylist2 has the value OX100, so that's what's passed. What am I doing here? So that's what's passed to list param is OX100. This is the same thing, or this array list of integer list param equals mylist2. That's the exact same thing that we do. Array list of integer mylist2 equals mylist. It's the exact same thing, except the assignment is split across a parameter declaration and an argument. But it's the same exact thing. List param just gets a reference to the array list that already exists, which means if inside the stack frame we make a change to this array list, mylist and mylist2 will see that change because they're still referring to the same list. Okay, so sum answer equals 0. Answer equals 0. We have a loop with I equals 0. I less than list param dot size. So list param dot size, we're calling size on this array list. It has 4 elements, so its size is 4. So 0 less than 4 is true, so we are going to run this list. So answer plus equals list param dot get I, list param dot get I, which is 0. Get the value at index 0, which is 10. So 0 plus 10 is 10. End of the body of the loop, so we increment I. Check the condition again. 1 less than 4 is true, so we run this line again. Answer plus equals list param dot get 1. So 9, 10 plus 9 is 19. Reassign it back to answer. Get to the end of the loop, increment I. 2 is less than 4, so we run it again. We're going to do list param of 2 is 8. So this is 27. Increment I, 3. 3 is less than 4, so we're going to run it again. Answer plus equals list param dot get of 3, which is 7. This goes up to 34. We increment I to 4. Check the condition. 4 less than 4 is false. So we're going to break out of the loop. I is removed from memory. And then we're going to return answer. So this whole stack frame ends, and answer, which is 34, gets stored into result. We go back to the main stack frame and print result to the screen 34. That's the end of our main method. That's the end of our oops, wrong button. That's the end of our program. That's the end of our trace. Which is the same exact output that we see here. And if let's just get the hash maps. I was going to try to change the example, but let's make sure we finish our content for the day. Hash map example. Hash map. And if you use, like, IntelliJ is usually good about auto importing for you, so it's pretty hard to miss your imports these days. But let's create a hash map. String to integer courses. As much as it breaks my heart, I'm gonna skip the bills example today that I do in the slides. But let's create a hash map that's going to course difficulty, that's going to map strings to integers. So hash map, this takes way less explanation than the array list does, just because most of the explanation is the same. I don't have to talk about imports again. I don't have to talk about type parameters again, or constructors, all that stuff. The keyword new, references, heap. We just talked about all that. But the one big difference is that a hash map takes 2 type parameters, because you can have different types for the keys and the values. So the keys of this hash map are going to be strings, and the values are going to be integers, and course difficulty. And if we want to add a key value pair to this, we're going to use the method put and we have to give it a key that matches the type of the keys and a value that matches the type of the values. And again, key value pairs themselves, the concept, going to assume that you're pretty well versed on them from 115. The big things to remember is that the order does not matter. So whatever order you add things to in this hash map, that order is not going to be preserved, and the keys cannot be duplicated. So if you add a duplicate key, it's going to override your old value. So to add something to this hash map, well, other than that, it's key value stores. That's what our hash map is going to be. It's like our dictionary in Python. It's your object in JavaScript. It's your map in C++. That's the data structure we're talking about. So the difficulty of CSE115, I'd say, maybe y'all can help me if you disagree. 4, 5, maybe 5 is a little more fair. Course difficulty, so we're adding in a key value pair. The key, CSE115, is a string, and the difficulty out of 10 as an integer. Dot put CSE116, I'm going to say is more like an 8. That put, and let's get 3 key value pairs here. CSE220, definitely a step up from 116. People can debate these. I'm sure people could debate these forever. Maybe 116 is more like a 7. Maybe this is even more like a 4. But I like this. This seems about right. And we'll skip 250. I don't want too many key value pairs here because I got to trace this whole thing. So that's how we add key value pairs into a hash map. And if actually, let's do it this way. So 4 dot put, just to emphasize this point, and then say I changed my mind. 115, I changed my mind, it's a 5. So I can't have duplicate keys in a key value pair, and I get the warning duplicate map key. So when I add the second key value pair, this is going to override the previous value that I had for that key. I can't have 2 key value pairs with the same key in them. So let's S out CSE115 is and then to get the value for a specific key, it is exactly get. So course difficulty dot get CSE115. CSE115 is a, how did I say this? Is a that out of 10. Then if we run this, excuse me, CSE115 is a 5 out of 10. That 4 was overwritten. So whenever we get the value for this key, it's going to be whatever the latest value we put in was. And usually, you just don't do this is kind of the answer. But if you do insert a new value, like for example, if you do want to update a value, this is how you would do it. Just insert the key value pair again with a matching key, and it will overwrite the old value. We're going to print the whole hash map to the screen. And then we want to know how to iterate over a hash map. I'm just curious. I got to see this. But now we want to know how to iterate. Oh, God damn it. We want to know how to iterate over a hash map. That's why I stick with the old example, because there's a point that I don't get to make here. Let me just try something. I don't think this is going to work for me, but... Oh my goodness, that worked. All right, perfect. No. Let's put spaces everywhere. Hey, I'm happy about that. Okay, so now let's talk about how to iterate over a hash map. And we can't use we can't use the for loop the way that we did with array lists. That's just not going to work for us. We have to do something different. And For that, we're going to use what Java calls its enhanced for loop, which I just call a for each loop, or what most of y'all will call is just a regular for loop, is a normal for loop. But the other one that we just saw is actually the regular for loop, and now this is the new cool one, but it's been around for like 20 years now, so it's not really new, and it really took over the for loop market. But this is going to look just like your Python for loops. This is the only type of for loop Python has. They don't even mess with the old stuff. So for string key in, we're going to use a colon that's pronounced as in. In Python, you literally type in, the word in. And we want to iterate over the keys of a hash map. We can go course difficulty dot get dot key set. That's going to give us a data structure with just the keys of the... How to make a cartoon? Why are you asking these questions? That's outside the scope of the course, how to make a cartoon. And that's going to iterate over just the keys of the course. So let's just S out the key. I mean, I assume you're not enrolled in the course. I assume you just stumbled upon the stream. If you're enrolled in the course, I'd like to know, give me more info or something. And I'll, or come to office hours if you're enrolled in the course. I'll chat about anything in office hours. If the queue's short, which this early in the semester it will be. And if we don't want to iterate over the keys, we have, there's one other option, iterate over the values. Values, course difficulty dot values. And that's going to give me just the values of the hash map. But that's really not enough. There's a third option we usually want, and that's iterating over the keys and values at the same time. So there's between a map and a hash map. This is a bit outside the scope of today, so I'll keep it kind of brief. But map is an interface that's implemented by hash map. So map in Java, map is an interface that specifies any operations that any map has to have, and then hash map is one implementation of that interface. So hash map is a specific map that we can actually create a new map of. Like, we can't create a new map. We're just not allowed to do that because there's no implementation. But hash map is an implementation of the map interface. And we can, for what it's worth, there are other types of maps. We could do a tree map. If we want a different map, it's still just a key value pair. It's giving me errors because I didn't import it, but we can use different types of maps. I just prefer hash map for the course. Actually, I don't prefer it. I don't care. But hash map is the one that we chose for the course, just because it's a pretty arbitrary decision which one we end up using. But hash map is the one we ended up using. But we just need some key value store, so we can talk about all our key value store stuff. A map in other languages is going to be different depending on the language. Is there a way I could loop over both in the single loop? Yeah, no problem, imposter. Yes, that's the third loop. There is special syntax to do this. I'm not a fan of that syntax. If you want to research entry sets and you want to use entry sets, go for it. Knock yourself out. I'm not going to show them because I think they're annoying because I always forget the syntax of them. And every time I want to use one, I have to look up the syntax and I don't know. It's just extra work. If you want keys and values, what I like to do, what my preference is iterate over the keys. And then the first line in your loop is to access the values. So course difficulty dot get the value at that key. Now I have key and value simultaneously, and I didn't have to memorize any wacky syntax or anything because I forget the entry set syntax every single time I use it. So this way I have both keys and values, and I can, let me grab this line right here. And key, I forgot my plus. Key is a value out of 10. Okay, let's run this, make sure everything makes sense. So we got our keys. So the first loop, we're iterating over only the keys, which are the course names. Second loop, we're iterating over only the values, which are the difficulty scores. And the third loop, we're iterating over both and saying the difficulty of each course. Now notice that order does not matter. This is one of our important points of key value pairs, is that the order does not matter. So even though I inserted 115, 116, then 220, when I'm printing or iterating, I get them in the order 116, 115, 220. So I'm always getting them out of order that I might have expected from the order that I inserted them in. Could you do string key course difficulty without the dot operator? No. Nope. So if I try, it's going to say not iterable. For each not applicable for type hash map. You can't iterate over a hash map. You can iterate over its keys or values, but you can't iterate over a hash map directly. It just doesn't have an iterator, so we're not allowed to do that. For what it's worth, you can. So now that we do know the enhanced loop, we can rewrite our array list code. So when we have an array list of, I'm pointing at the screen like you can see, when we have our array list of integers, we can actually do for int. And remember, I'm always using the primitive type unless I have to use the class type. So even when I'm doing this, for int I in list param, I can actually iterate over my values in an array list the same way. And then I wouldn't use the dot operator here because array lists do have iterators, and I can just directly iterate over them. What about arrays? I don't like using arrays in 116, but you can. Like we have this array list of args for string arg in args. Like I can do that with a plain old array too. But I don't like messing with arrays. It's just an extra thing that y'all have to know if we mess with arrays. But yeah, you can do this enhanced loop or for each loop with arrays as well. And importantly, what you do want to use throughout the semester is array list. But I want to make sure I show you this. That's why this is in the example. Is that sometimes you do need the indices. You need the indices and the values. So I want to make sure I show you this way that's more powerful than the other way, because this way you have no way of accessing the index of the value. You only have the value. But this way you have index and value. So when you do need that, if you know how to use the loop this way, you always have that option. If you only know how to iterate this way, you have less power. You're less powerful. Then when you do need the index, you just can't. You can't do it. You call in a better programmer. You want to be that better programmer. All right. All right, so let's go through this. And since I named it course difficulty, it's such a long name, I have to resize things here. So let's go through this. We got time. We got this. Every Java program starts with main. Course difficulty, which thankfully I only have to type once. Course difficulty is going to get a new hash map. So I have a hash map on the heap. Doesn't have anything in it yet. We got OX100, OX100. I can't even resize that. I just don't like having the bar on there. And we're going to insert some key value pairs into this thing. So course difficulty dot put. We're calling the put method on this hash map here. And we're going to get CSE115. CSE115 gets the value 4. And we're going to put 116.8. CSE116.8, CSE129. And then when we put the value CSE115.5, CSE115 already exists as a key. So when we put this key value pair, we're actually updating the value at that key CSE115. So we can't have duplicate keys. The extra key is going to overwrite the old value. So 4 is no longer in this hash map at all. I'm not typing all that. We get to our print line. Oh, this mouse. Not the mouse, but the surface I'm using is a 5 out of 10. Okay, and then we're going to print out this hash map. We saw the syntax in IntelliJ, but let's do this again. CSE115 equals, I wish it used colons, but it uses equals, 5, comma, CSE116 equals 8, CSE220 equals 9. So at this point, I just want to point this out. The order does not matter with hash maps. We saw the order is actually going to be CSE116, then 115, then 220. I missed a space here. But when I'm doing my trace, I'm not going to do that. I'm just going to put them in the order that I inserted them in the hash map. And you can do this too. This is the recommended way. It's what pretty much every student has ever done. But the order is arbitrary. Order doesn't matter, which means for your traces, you can choose whatever order you want to print them out, to iterate over them when we're iterating over the keys and values. You can do it in any order you want for a hash map because there's no reasonable way for you to predict what that order is going to be when it actually runs as a Java program. The order actually depends, since we're using a hash map, the order depends on the hash values of the keys, which you're not going to have any reasonable way to predict that during a quiz. So you can choose any order you want. And the simplest order that will lead to the least mistakes is just going in the order that they're inserted in. If you go in a different order, it's just easier for you to make a little mistake where you went in you missed a value where you duplicated one. So your trace doesn't have to be 100% accurate when you have a hash map because of the ordering. And any quiz that's going to have a hash map, which I might just not even give you a hash map on any quizzes, but if any quiz has a hash map, it'll be set up in a way where the order that you iterate over the values isn't going to affect the final result. So I'm not going to do like for each and then keep doing a subtraction or it's a bad example, like a division. Actually, subtraction works. Like a subtraction or division. It's going to be some commutative operator. Okay. And we're ready for our first loop. I'm going to create my code block, the variable key, which is going to iterate over the key set. So I'm going to look at the keys of my hash map, and it's going to go through the keys one at a time. So let's go in the order in which they were inserted. CSE115, print it to the screen. CSE space 115. We get to the end of the loop. So now there's no increment. A lot of the minutia is simplified with this loop, this for each loop. We're iterating over the key set, so we advance to the next value in the key set, CSE116. Print it to the screen. And advance to the next value in the key set, CSE220. Print CSE220. And we also don't have any awkward situation where the variable gets the next value that doesn't actually execute with the body of the loop. We don't have any of that with a for each loop. The loop is just over after we handle the last element in the data structure. So that's just the end of that loop. Move on to the next one, which is quite similar, except we're going to do the values instead. So value over the values is going to be 5. Print 5. need more I/O lines here. There we go. Print 5, advance to the next value, which is 8. Print 8. Advance to the next value, 9. Print 9. And that's the end of that loop. We iterated over all of the values of this data structure, all 3 of them. So this block is over. Then we have one more block, one more loop. We have the iteration variable key, which is going to iterate over the key set. So CSE115 to start. The first line is going to access the value. So a new variable value, which is going to course difficulty dot get key, which is CSE115, which, oh no. Missed a bunch of quotes here. Again, this is a very minor thing. You would never fail a quiz for missing that, but I want to be 100% accurate in lectures. And value is going to get the value, course difficulty dot get the value at key, which is CSE115, so that's going to result to 5. And notice that since we have code blocks, key and value, these previous variables were destroyed when their corresponding code blocks ended. So that means when I'm using key and value again in this last code block, that's perfectly valid. I'm allowed to do that because normally I would get duplicate variables being declared. I would get errors for that. But I'm not getting errors because key and value, these first ones, don't exist anymore. They're literally removed from memory. They've been deleted, so I don't have to worry about any name conflicts with them. So I'm able to reuse key and value. That's how I'm getting away with reusing these names. So when we like our loops with our looping variable being I, we can just have every loop have a looping variable I, unless they're nested loops. If I have a loop inside a loop, I have to use different variables. But if it's a loop, then a loop, then a loop, then a loop, I can use I every single time if I want. So it's one nice thing about the fact that the variables are destroyed at the end of a code block. Okay, and then we're printing to the screen. CSE115 is a 5 out of 10. End of the loop. So we advance to the next key, CSE116. We get the value, which is 8. We print to the screen. CSE116 is a 8 of 10. We get to the end of the loop. We go to the next key, 220. Get its value, which is 9. CSE220 is a 9 of 10. We iterated over all the keys, so this loop is over. We get to the end of the main method, so this program is over. That's hash maps. It looks like there are no more questions about the trace. If there are, please let me know. But we got 12 minutes. I want to muck around in IntelliJ and emphasize some of the key points that we made there. First of all, the output's the same, just different order. Order doesn't matter in hash maps, or is not really controllable. If the order matters to you, don't use a hash map. Is the end story to that. And notice that key and value are also destroyed at the end of this last one. So if I want to create string key equals CSE250, string value, int value. You have to decide how hard 250 is. It's definitely harder than 116. I think it's a little easier than 220. We bump Let's not bump 220 up. Let's just give it a 9. We'll call it the same as 220. I think that's mostly fair. Maybe 116 would have to be bumped down to a 7 just so I can say it's 8 and 9 for 250 and 220. I'm overthinking it though. So we can reuse these variables again because all the previous instances of these variable names have been destroyed. But if I try to do string key equals CSE191, I can't do that. I can't create another duplicate variable because that key already exists. When you're specifying the type and a variable name, that means I'm creating a new variable, and you can't have two variables with the same name in the same stack frame at the same time. When they're in different code blocks, they're not in existence at the same time. This key is destroyed before this key is created, so we don't have to worry about a name conflict there. But here, this key is still in memory, still in the stack frame when we declare this key, so that's going to give us an error because we can't have two variables with the same name in the same stack frame at the same time. And with that, I think I hit all the points I wanted to make with these examples, and it's time to just kind of mess around in IntelliJ and do more like tips and things. The first thing I want to make sure that I say, I think I have this structured in Tuesday's lecture, but the sooner I can say this, the better, is if we have an array list, yeah, whatever, I'll put it right here. If we have an array list, we're creating an array list, and say you're setting up your test cases for the average method. That's the first time where this really comes up. And you create your array list, and then you do mylist.add 4. And then you duplicate this, Control D, and you want a test case with like 4, 5, 6, 7. And you end up doing this. And then let's, just for clarity, let's get rid of all this. So this is what you end up doing. There is an easier way. It's a common question I get, and for good reason. There's an easier way to do this. Instead of adding them one line at a time, we can do something like this. We can do arrays.asList, and that lets us specify, oh, I forgot what values I just used. Was it 6, 7, 8, and 9? 4, 5. Yeah, I literally forgot. 4, 5, 6, 7. Arrays.asList, and I'm getting an error here because I did not import arrays. So I'm going to import it. So you do have to import that if you get the error. But if you do arrays.asList, then you can have any comma-separated list of values and initialize your array list to all those values all at once. So if I print this out just as a proof that we actually did something here, that array list is going to have all those values in it. So it's a lot cleaner to be able to set up your test cases for the average method. And with that, what I want to do the rest of it, actually I don't want to muck around in IntelliJ. I lied. What I want to do is, go to the course website and talk about programming test 1, because this is out there, this is ready for you. And you're asked to write these 3 methods and write tests for them. The tests you can't really quite do yet, but writing the methods themselves, you have everything you need to write these methods right now after today's lecture. You have all the tools you need to write these. I want to give another hint for sum of digits that I alluded to earlier. But the testing, if you're ready for the testing, we're not covering that until Tuesday, but just like I said last time, I recommend that you do watch that lecture. If you're ready for it, you're comfortable with everything we talked about this week, I would go ahead and watch that lecture from last summer and learn the syntax of unit testing. There's not too much to it. There's a lot of little things, little nuances that I have to talk about in lecture, but just to get the syntax of how to set up your testing isn't too crazy. So you can start writing your tests for the things that you definitely know what's up with. And then if you have some errors, then you have to watch the lecture to get all the nuance, or just watch the whole lecture, whatever. But but I would get ahead and watch that instead of sitting idle for the next 5 days just waiting for that. Then you can finish task 1, because this course is about to get really intense. Once we hit next Tuesday, the course is really relentless. You're going to have programming test 1 out, and then in 2 days, that expected deadline hits, and that same day, task 2 is out. Like, you're going to be ready for task 2, which is due in 2 days, and every lecture is like that. Every lecture is going to give you a task and expect you to do it in 2 days. There's just a relentless barrage of tasks, which is kind of the way it has to be in the summer course. There's not really a better way to structure it. It's just a lot in a short amount of time. I mean, the deadlines could be different and stuff. You can debate things like that. But in 6 weeks, you have to write a lot of code to prove that you've completed the learning objectives. So I would not sit idle this week. If this week you're just waiting till Tuesday to start programming task 1, there's really no time to take a break after that. It's just going to be 5 weeks of just nonstop tasks, including a midterm. Luckily, we have a lecture off right before the midterm, so you do have some extra time to study and complete your task 5 for the midterm. But yeah, it's going to start hitting really hard starting on Tuesday. So I would get ahead while I can if I were you. Some of you won't do it. It's fine. Make your own decisions. But that's my advice. That's my recommendation. Get ahead of things. Definitely don't fall behind on things. So with task 1, it's these 3 methods, and I want to go over what the methods are. First is the average method, and all 3 of these are pretty much the accumulator pattern. I am making sure you can write 115 level code in Java in the 116 language. That's what task 1 is all about, and also getting comfortable with testing. So when you're testing the average method, that's where using arrays.asList makes it a lot simpler to create these test cases. But the method itself, take an array list of doubles and return the average of all the values in that array list. Should be very simple to anyone who's registered for a second course in computer science. The logic of how to do that, you better have down. If you need help computing the average of an array list of doubles, I'm concerned. I mean, we'll help you in office hours for sure, but that's you're going to have a tough time catching up because you're already behind. I assume that doesn't apply to anyone here. You should all be able to compute the average of some data structure. You should have that down. And I'll specify if there's some edge cases that need to be handled. If the array list is empty, just return 0.0. And then I'm given some sample test cases here. When you do get to the point of testing, coding up at least the test cases that are given. Like, you're allowed to just take these test cases and write them in code. It's the very first time you're writing tests, so I give you the samples, code up the samples, and use those as your starting point for your testing. So you should at least have these 4. If you don't have these 4 and you come to office hours and say, why does Autolab not like my testing? The first thing I'm going to say is, well, at least code up those 4. I gave them to you. Like, use the ones that I gave to you for free. And then when we get to sum of digits, this one is a little trickier. This is the trickiest question, in my opinion, at least out of the 3, by a pretty wide margin, if you just try to tackle the problem without any hints. So I do give hints for this one. I gave them earlier in the lecture. I'll give them right now. I'll give a more thorough one. So we have the modulo operator, which is going to give you just the remainder of a division operation and not the quotient, and integer division, which gives you just the quotient and not the remainder. If we combine these 2 things, we can do sum of digits pretty easily. So if we have 1, 2, 3, and we take this number modulo 10, what that'll give us is just the ones digit. It'll give us just this 3. Then you have your accumulator pattern, so you add that 3 to your accumulator variable, and then divide the whole thing by 10 using integer division. What that does is effectively erase that ones digit, and then you'll be left with just 12. So you take 12, you modulo 10 to get just the 2, add that to your accumulator, and then divide by 10 again. That gives you just 1. Modulo 10, that gives you 1. Add that to your accumulator. divide by 10, that gives you 0. And once your number is 0, that's how you know you're done. So if you're repeating that process well, your number is not 0, you'll be able to sum up the digits quite easily. So that's my recommended strat. I basically gave away the answer to it right there. That's how you want to tackle sum of digits. And again, code at least these 3 test cases. You'll be doing pretty well with those 3 test cases. Best key. This is one we haven't talked about testing yet, so a little of this I'll be getting ahead. But best key, you're given a hash map of strings to ints, and you want to return a key with the highest value. Again, that's a min-max problem. Give the key with the highest value. You're going to have to iterate over the keys and values at the same time, check the values, and then store the keys. But where it becomes a testing thing is sometimes the best key will be tied. So in this example, both cat and dog are valid outputs. One of the big mistakes I see students make, not really, it is a mistake, but it's what you're learning on this one. This is how it's set up, is to get you to understand this part, is that when there are multiple correct answers, you have to accept either correct answer in your tests. And what a lot of students do is their code will return cat, so their tests will expect cat, and any code that returns dog, it will say that is incorrect code and it will fail the test. But then my code in Autolab, if it returns dog and you're expecting cat, and you say, no, you return dog, that's wrong because I'm expecting cat, well, that's a bad test. And the error in Autolab will say your test rejected a correct solution. So you have to write your tests in a way that if the method returns either cat or dog in this test case, it accepts that and passes your test. And we're at 1:31, so that's all the time I got. I gotta shut it down. I never liked when professors went over, so I don't want to do that. I already went over by a minute. If you're coming to office hours, I'll be in office hours in half an hour. I'm going to take a quick break and then head over there. So if you have any questions, see me in office hours, and we'll chat there. All right. Take care, everyone. Have a good one, and I'll see you Tuesday if I don't see you in office hours.